folly. I hope you are well rested. Even puppies need a nap after learning KMP. Logarithmic abilities are flowering. Heralding a new week. Welcome back.
Indeed, I am overjoyed to see all of your smiling faces and to see that we've actually retained a bulk of the class post the mid-semester break. So I think that is a sign that things are going well for all of us. Don't forget, you have an assignment due soon, so if you haven't started, as I really hope you have, now is the time. You've got till Friday at 4 p.m., so keep up with the work, keep up with the Grok questions, the Ed STEM questions. We're here to help you, and I'm looking forward to our last few weeks together. Just a reminder, I am only here for this week and next week, and then I go on a trip to America to hopefully bring back some more exciting algorithmic insights from the forefront of whatever is happening overseas, and then I'll be back again for the last week to finish things off for you. As always, today we've got a new figure for the week. This is Barbara Liskov, who was born in 1939 and is fortunately still alive. She was responsible for many important developments in programming languages. In particular, she was the mother of object-oriented programming development and is responsible for all these languages that you see above. Later in this week, we're going to see elements of the C programming language that overlap with some object-oriented programming languages. And we'll have a very short discussion about what that means for the way we store data. And this was Barbara Liskov's one of her main contributions, was to conceptualize the way that we store data inside computers and to formalize it. For this, she won the 2008 Turing Award and is still a professor at the Massachusetts Institute of Technology, MIT. To take us back to our content, this is where we were at the end of the break. We had come up with a way to efficiently find patterns by trading off some work ahead of time in order to make our operations faster when we had to come and repeat them multiple times. So we would process our string ahead of time with the advanced knowledge that at some point in the future we were going to use it for pattern search. If our pattern was she sells shells, as we have up there, we would construct an array containing each of the potential suffixes for the string, starting with she sells shells, which is a suffix that contains all the characters, all the way to a suffix that contains only a blank marker character. That's what we're using the $sign there for. It's just to make implementations easier and represents that we have no characters left in our suffix. To build our array, we have at every position I, we have a string t of I, or we could alternately represent the suffix as the suffix that begins at the ith place. And so this is going to be our array S. Our array S contains the index at which our suffix starts. This might seem trivial because when we have an unsorted version of this array, our index I and the contents of Si are the same thing. But when we sort this, if we sorted T of I in lexicographic order, so that the one that comes, the suffix that comes first at the alphabet is the first element in the array, and we sort S of I the same way, we match it up, so we leave S of I and Ti, we leave the two matching pairs where they are with each other, then we'll have a difference between the index in our final array and the contents of Si and the contents of Ti. So what is a fast way of actually achieving this sorting that we need to do? Well, if we want to sort our array here, we could do our normal quicksort, but quicksort has some associated problems with it. In particular, quicksort's runtime is n log n, where n is the number of items in the set. However, this assumes that each comparison only takes one operation. If it only takes one operation, n log n is our running time. However, when we have a string, let's say we have a string of size, an array of strings of size L, how long does it take us to compare two strings of size L? And this is for the audience, but we probably don't need a microphone. Just shout it out if you know. If we have two strings of size L, what is the big O running time of how long it takes to compare to see which of these two strings is bigger on average? So if the strings are the same all the way to L minus 1, then we have to look at L minus 1 characters in one of them and L minus 1 characters in the other, and only at the end we figure it out. But on average, if the strings are random, do we expect that they'll be all the same up till the end, yes or no? No, they won't be the same most likely. Will they be the same in the first character? Let's say we have 26 characters in our alphabet. What's the chance that they match on the first character? So let's give the microphone to Noah back there so we can have a bit of a conversation around this one.
The chances are low.
So if we have 26 characters in the alphabet and we choose one letter randomly from the alphabet for the start of both of our strings, what's the chance that they'll match?
1 in 26.
Yeah, 1 in 26 chance of picking the first one. And then so if we have picked the letter A and we have 26 possible letters, the chance that the second letter A, assuming it's random as well, is also 1 in 26. And this goes for every letter in the alphabet. Now what if we're talking about just binary ones and zeros?
1 in 2.
1 and 2. So if everything is 1 and 2, we're going to eventually end up averaging out over the length of the entire string, and we'll get an average case running time of roughly bounded by the length of the string. So we're not going to do the exact maths to work this out, but we know that at least when we have when we have two strings of size L, the comparison time is going to be big O of L. It's not going to take us more than two L checks over characters to see if they are equal or which one's bigger. But now if we feed this back into quicksort, for each time that we do our quicksort, we're going to have to do for each time we do a comparison, instead of being able to compare integers instantly, we'll have to do L work. So this would give us Ln log n. But there's an additional step, an additional inference we can make. If we're building a suffix array and our string is of size n, how many items are we going to have in our suffix array? We're going to have n items in the suffix array as well. So we know that the maximum length of a string that we might compare is of length n as well, because it starts at n and we have n items, which gives us n squared log n as the running time for quicksort. Now it is possible with some adjustments to change this to n log squared n, which would be an improvement over the original quicksort, but it's still not that fast. So we turn to a variant of quicksort to make this a little better, and this we'll go through now. This is the pseudocode for ternary quicksort. It's very similar to our prior quicksort, only we now partition on a single letter of the string, where we would previously partition on the value of a pivot. So if you're, instead of having to compare the whole string to the pivot, you just compare the string to the first letter. And then what we do is we sort into 3 buckets: everything that matches the pivot, which would be the first letter of our string, everything that is earlier lexicographically than the pivot, than the first letter of our comparison string, and everything after. But that sounds kind of abstract. Let's look at how this works with a demo. If we have the array of strings, she sells seashells by the seashore, the cells she sells are surely seashells. Man, that's a bit of a tongue twister. Let's choose the first letter of the first element as our pivot for ternary quicksort. Remember, we have at the top here, pick a pivot and then compare to the pivot. So if our pivot is S, we go through our list of strings and check to see which strings start with a letter that's before S, which strings start with a letter that's the same as S, and which strings start with a letter that's after S. And we group these into the 3 piles accordingly. However, this hasn't solved our overall lexicographic sorting problem. All it's done is told us which groups are ahead of which groups. So who could see what we might do next to further sort these? And you've just seen the pseudocode, but obviously it's a little hard to process. So what would be an intuition of the next thing that we'd do?
Compare the next character.
Wider, right? How do you say your name again?
Wider.
Wider, okay. So say that into the microphone for everyone and for the Zoomies to hear and for the recording.
And then we compare the next character.
Yeah, so we could compare the next character along, but do we have to compare the next character, say we're looking at the letter E in seashells and we're pivoting on that. Should we do that for all the groups?
No, we should do each group individually.
Yeah, we can do each group individually, saving ourselves some work because we already know that by and are before seashells and she. So let's sort each of these groups individually by looking at the next character in each of the groups. So for each of the groups, we choose a different partitioning item. In the first group, we would now choose the first letter of the word by, and then do our partitioning again. So by, the letter B is in a group with a word that starts with the letter A. And what we can do then is we put the word with the letter A before the word with the letter B. So that's our first group sorted. In the next group, we choose the letter E as our pivot for that group. And then we sort everything out. You can see in the fourth column here, everything with the E gets, with the next letter before the E gets sorted into the top group. Everything with the E gets sorted into the next group, and everything with a letter after E is the second letter gets sorted into the third group. And then the bottom group doesn't need any sorting because they're already all equal. Finally, we get up to the last group. Now we're looking at the fourth letter along, so our new pivot is S, and we group them accordingly. Everything with the S gets put in the middle of everything with a fourth letter that is later than S, and after everything that has a fourth letter that's earlier than S. So the letter C, the word C doesn't have a fourth letter, so we just put that beforehand because we'll say that blank is earlier than not blank. And then seashells and seashells get put after the word C, and we're done with that component. Then if one was to keep going, you'll see that we still have some work to do with the shells she, surely, sure, and she, but the process just repeats itself. This should give you an idea of how ternary quicksort works. So if we're adding n strings of length L into the array, that's going to give us n work. But what we really care about for these algorithms is the number of comparisons we do. The amount of work we do up front is just going to be the length of the string once, and so that's probably not going to dominate. It's going to be the sorting time that dominates. So this gives us n log n character comparisons on average through a more sophisticated analysis that we won't go into too much depth on. Why does this work? Again, much like our KMP algorithm, the goal here is to avoid repeated work. We don't want to recompare common prefixes that we've already compared before. If you look in our, at the overall structure of our algorithm, you could see that it would be possible, were we doing naive quicksort, to have to compare the starts all the way from the start of a string to the end of a string multiple times across numerous strings. By breaking the problem up in this way and by only comparing one letter at a time and partitioning around the letters, we save ourselves having to compare the entire string and then the entire string and then the entire string for all the different elements in our array. But why does this work? Well, we have a limited alphabet size, and knowing that we have a limited alphabet size and that we have structure in our words allows us to change the data structures that we use and the algorithms that we use to deal with the actual characteristics of our input rather than assuming a totally random input that comes from any possible set of symbols. And what I mean by symbol is a possible letter in the alphabet. So if we don't know how many letters there are in the alphabet and we could keep getting new letters that we'd never seen before, some of the algorithms in this class wouldn't work anymore. One of the really interesting things about algorithmic design is taking the structure of your data, pairing it with a data structure, and pairing the data structure with an algorithm that leverages that data structure to give us advantages that we wouldn't ordinarily have otherwise. Can we do even better than this? I think by the look of the eyebrows, the answer is probably yes. We also have fancy construction algorithms for our suffix array. Previously, our idea was to do these sortings, so what we do is we fill the array first with all the suffixes, and then our sort is n log n, or n squared log n, or n log squared n. Can we actually build the suffix array in linear time? This would save us a whole lot of work. Here is a discussion on suffix construction from 2007 by Professor Andrew Turpin, and this quote is actually referring to the study. I think it sets things out really nicely about our holy grail of suffix array construction, what we're looking for at the end of the day. So you'll see here an optimal suffix array construction algorithm, so that's a SARCA, fulfills 3 requirements. First, the algorithm should run in asymptotic minimal worst case time. So what is the best big O bound that we can possibly find for the problem? So this would be linear time in an optimal way. Second, an algorithm should run fast in practice too. Note that this is actually distinct from big O time. You can have a big O time that's really good, but when it actually comes to running it on a real program, maybe the constant number in front of, like, let's say it's big O of n, maybe the actual function is close to like 10 million n, which is still big O of n, but that might run really slowly. Additionally, when implementing something on a computer, you have limitations like the size of the computer's memory, the way that the processor works. So a second criterion for having a really good algorithm in the real world is that not only should the big O time be good, but the actual practical running time should be really good as well. Finally, the algorithm should consume as less extra space in addition to the text and the suffix array as possible. So when you're constructing the suffix array, you're obviously going to use some more of the computer's memory while you're building up the suffix array. You'll have extra variables you store, you're moving things around, and these will all take computer storage. So in order to make the algorithm practical, it actually has to use a small amount of memory such that it's efficient for the computer and actually fits within the computer's memory. At some point this semester, we might also get to talking about different speeds of different parts of the computer's memory, and this also affects whether an algorithm runs fast in practice. So in 2007, Andrew Turpin, who was then at RMIT and now at Melbourne Uni, was saying, well, we don't actually know if we can achieve all these things for a suffix array. And up until 2016, these were still very much open questions. We had suffix array construction algorithms that fulfilled some of these criteria, but nothing that would fulfill all of them. Fast forward a little bit, and we have made some progress. This is a paper from later in 2016 from some authors in Tsinghua University and Xijian University. They have the following 3 claims about their suffix array construction algorithm that they were able to make. Firstly, it only uses O of 1 extra space to build the construction algorithm. So it uses a fixed amount of extra space to build the suffix array. Next, it is an in-place linear time algorithm for read-only integer alphabets with big O of n. So we're not going to go into too much depth there, but the basic idea is that for a fixed set of, for a fixed alphabet, they were able to build a big O of n algorithm, and they were also able to do a general in-place optimal O of n log n algorithm. So we have almost all 3 of these, and this was combined with a fairly fast in-practice version of the algorithm as well. So certainly making progress. We haven't solved the problem for the complete general class of problems, but this just goes to show you that we're always making advances on what seem like fairly standard first year foundations of algorithms. These still do change over time, and there's plenty of room for you to get involved in making these new algorithms. This is a chart of just how it's evolved over time. You can see a whole series of different papers which each use different amounts of time and different amount of workspace to complete essentially the same task. Improvements are still happening. Just because we've found a few pretty good algorithms doesn't mean the work is done. Some things that we might want to do is find a way to parallelize the computation. So if I have 10 computers rather than just 1, is there a way that I can build the suffix array even faster by splitting up the work across the different computers? Are there faster implementations? So now that I've got a fairly good algorithm, how can I optimize the algorithm such that in the real world it works really fast as well? And then what happens if our suffix array gets really, really large, like many, many gigabytes, larger than a computer's active working memory? Is there an algorithm that we can build that's efficient even when we have to use memory that's outside of the computer's main memory? Perhaps it has to go back to the hard drive, which is a fairly slow operation to do. So for our overall question of how efficient is suffix array pattern searching, we have our two parts. We have our construction, which we now see can be done in big O of n, and we have our search, which can be done in m log n because this is just binary search. Binary search where if our pattern is of length m, we have to, at each step of our binary search, check the m letters to see if we've found the one we want, and then log n because there are n items in our array, and a binary search takes log n time, assuming that each comparison only takes O of 1 work. But because our comparison takes O of m work, where m is the length of the pattern we're searching for, overall we get m log n. So what we'd do to actually do this in practice is we'd probably have many searches through our index over and over a period of time. So we'd do all our upfront O of n work, and then we'd have our very fast searches that we can do over and over and over, illustrating the efficiency of this approach for handling repeated searches by trading off some upfront work for fast repeated work. This is going to be a recurring lesson that we've seen once, we've seen again now, and we'll probably see a few more times. Trade the repeated work, instead do some work up front, instead of doing lots and lots of repeated work. We've got a new problem now to set our sights on that will take the majority of the rest of today, or some of the rest of today's lecture, before moving on to some exciting new material on new data structures. Our new problem is now, how do we efficiently find the context of a key phrase? Why might we want to find the context of a key phrase and not just the phrase itself? Liam. That. Okay, I haven't caught your name before, I don't think.
I don't think I have the answer.
It's okay. What was your name?
I'm Ming.
Ming.
Yeah.
Okay, so let's say that I am doing a Google search. Why might I want to know the context of where my phrase appears and not just the phrase itself?
I think it's for more accurate suggestions.
Yeah, so one thing could be you get accurate suggestions. Let's say I type in what's a really famous song? Yellow Submarine, there we go. So let's say I put in the Google search box, lived a man who sailed the seas. Now I'm not sure if you know the lyrics to Yellow Submarine or not, but this is precisely the question. If I type in lived a man who sailed the seas, why might you want to know what goes around that? Assuming that that's our lyric.
Because there might be infinite number of searches.
Okay. What was your name?
Because the amount of searches might be like really high.
And what was your name again, sir?
Mahi.
Maheen. So Maheen has one reason, keep holding the microphone for a second, that there might be a whole lot of different possible searches that all match this thing. Well, that's true, and how will having some context help? So think of our lyric again. What do I really want to know when I'm searching that lyric?
The name of the song.
I probably want to know the name of the song, and if I'm searching some of the lyrics, what else would I probably want to know? If I can only remember 4 of the words to the song, what do I probably want to know?
The rest of the...
The rest of the song. And so if I search lived a man who sailed the seas, what I probably want to see is in the town that I was born, lived a man who sailed the seas, which is the first part of the lyric of Yellow Submarine. And so by having context, we can very efficiently get not only the general where it appears in a document, but we also want to know some of the information that surrounds it, and doing this efficiently can save us a lot of time. If you type in Google, let's see what happens. Let's type in a search. And you'll see that having the context allows me to very efficiently get more information about the thing that I was searching for without actually having to click on the links. So I would find out very quickly that A Shortcut to Mushrooms is the 4th chapter of the 1st book of the Fellowship of the Ring without actually having to click on the document and then scanning through and seeing where it appears. So even knowing where it appears is sometimes not enough. You might also want to know the context that surrounds it. Thank you very much, Ming and Maheen. You might have to remind me a few times. You've seen me do it with everyone else, and it'll be your turn soon enough. Thank you, Liam. So there are a few ways that we could possibly do this. The most obvious way would just be every time we have a word, we store all of the context along with it. Now, this doesn't seem very efficient. I'll take the microphone back again. Why might this be a bad idea to store all the context that surrounds every search phrase? Okay. So what we were looking for is, let's say I have a lyric for a song, and I want to find the words that are near it. Why might it be a bad idea when I'm building my data structure to have all the context stored for every single possible word in my index?
Maybe just need a part of it to search for the whole thing.
Yeah, so if I am searching for a phrase in The Lord of the Rings, is it likely that I'm going to want to read the entire Lord of the Rings when I just search for that phrase?
No.
Yeah, so what might be more useful?
Just to store a part of.
Yeah, just to store a little bit of the context. And what was your name? Joyce. Joyce. Oh, yes, sorry. Sometimes I miss it with the masks. So we obviously don't need to store the entire context along, and this would be not only a bad idea because it gives us extraneous information, but it's probably a bad idea as well because then the size of my storage is going to be really large. If for every word in The Lord of the Rings I'm storing the context of the entire rest of the book, this is going to be a giant amount of storage really, really fast. So what Joyce's suggestion was is that we only store a part of the context here. In this case, we are going to store the 2 words before and after. And if you're Google, you might store the 30 words before and after or the 20 words before and after. And this is a trade-off between the efficiency of searching and the efficiency and the amount of storage and time that it takes you to both do your construction and actually store this in your database or whatever it happens to be. So you can see for each of these words, the word, say our search word is the red word in the middle. We're storing a window of 2 words before and after, and this provides us one nice trade-off between the quantity that we have to store and our ability to quickly and flexibly look things up. This is another illustration of how indexing is a really powerful tool to do this trade-off behavior, to trade off between pre-computation and storage and efficiency of our searches. This can also be done for many other algorithms, as we'll see throughout the semester. Another alternative that we could do instead of storing each of these words along with our key phrase, so instead of storing seashells by and then the sea, instead of storing all of those for each and every word, our 2-word context, we could store all the places where the keyword occurs in the string, and then when we need to do a lookup, we can go back to the original string and just quickly recompute what are the 2 words before and after. Why might this be a bad idea for Google, even if it's a good idea in general? So this is a bit of a trickier question. It hinges more on your understanding of how Google kind of builds itself. Okay, Boxiang, we haven't heard from you in a little, and you're giving me a look.
What's the question?
So the question is, one way that we could do this keyword and context thing, if I search the word by, and I want to get the context seashells and the sea, and I'm Google, why is it a better idea potentially to store the context rather than storing the place on the internet where you found the word by? So I could either say, oh, I remember the word by is at seashells.com, and then you go to the place and look up the context, or you can store the words in your database. Why is this option a better option than that option if you're a search engine?
I guess
I guess the address might change when you crawl the website again.
So one thing is the address might change and you might want to preserve the information, but a more important reason is that going to the web page and finding the text is a fairly expensive operation, and Google is trying to optimize on storing things ahead of time. Storage for Google is very cheap, whereas it's expensive to go and get the context. But there are other scenarios, say that you have, don't worry about turning it off, we've got a new setup this time. But there are other instances, say when you're searching through a genetic code, where the code might just be the entire genetic code might just be sitting on your computer. It's expensive to do the storage and very quick to look up the context. And so this gives us a sense of different trade-offs that you can make based on the characteristics of your real-world problem. If the thing that you have to go and, if your source string that you have to go and look up is difficult to look up, then maybe store it. If your source string is easy to look up, but you're limited on storage, maybe store the context. Here is another example of this type of indexing where one might want to do this kind of storage mechanism of storing the location in which the context can be found instead of storing the context itself. This is the back of an early 1900s reference book called the Book of Knowledge, and you can see if we look up all instances of the word Portugal in the text, or at least the important instances of the word Portugal, you can see that it occurs in volume 1, page 272, volume 17, 5370, and then all throughout all those different sections. Now here you'd think it obviously makes sense that we store the references to the context and not the context itself, because for us it would take a lot of reading through to find what we were actually looking for if we had all the context present under the location of the index in our index. Instead, for this particular scenario, it makes sense to just store the locations, and then once we know which location we're interested in, we can then go and pull it out of the other book. This concludes more or less our discussion of indexing for the class. We may revisit it later in semester, but the key takeaways here involve the different sorts of trade-offs we can make when building data structures, and in particular for string search. This is an example of building one of the inverted indices on a program that we don't actually supply for the class, but you can see for our seashells by the seashore, we create an inverted index that's just pretty similar to the one we saw there. It's a grok exercise, okay. Well, that would be why. Our summary for string sorting is that we actually can sort strings in linear time by doing these very fancy mechanisms and under a potentially restrictive set of assumptions. We can't sort any string in linear time. This would be bounded by what we've already learned about the optimal time for searching. However, with additional knowledge of the structure of our strings, we can sometimes get it down to linear time. Real-world data generally has structure, and this is something you should look for when designing your algorithms. What is the structure of my real-world data that I can then leverage to turn it into an efficient algorithm? Combine, as I said before, the natural structure with the data structures and the specialized algorithms, and that's the recipe for overall efficiency. Now we've got a bit of an interlude to some C syntax that will give us some more powerful tools for building even better and bigger data structures. So I need one more new volunteer from the audience, someone I haven't spoken to. If I haven't called you out before, please put up your hand. Don't be shy, come on. Need at least one hand. Who is new? Okay, I'm trying to think of who I haven't spoken to. Have we chatted? No. Okay. That was very bad hand raising. What was your name?
Josh.
Josh. So tell us a little bit about yourself. Give a short 3-line biography that you're comfortable with the class knowing.
My name is Josh. I'm 26 today, actually.
Oh, happy birthday. That
Thank
was
you.
an excellent pick on my part.
Okay. I'm from South Africa.
Okay, and okay, that gives us our 3 questions. Now, let's say that we want to store this biographical information about you in our program. What would be one way we could do it?
We just, make an array with all my information, one after each other.
Would this work in C? Is your name the same type as your age?
No, it's not.
And what's our restriction in C? Does C let us have multiple variable types within the same array?
No.
Okay, so what would be another way that we could store this information?
Not sure.
So we have 3 different data points here.
Yeah.
And could we store it in 3 different variables?
Sure.
So what would be those 3 variables?
It would be, my name, which is a string, Haldan, which we can use, an integer, and where I'm from, which is a string again.
Yep. So that would be one way of doing it. Now pass the microphone to your left.
She's out of the class.
Doesn't matter.
Yeah, okay, here you go.
Hey, what's your name?
Laura.
Laura. Pleasure to meet you, Laura. So give us 3 facts about yourself.
I'm Laura. I'm 27 and I'm from Tasmania.
Okay. Well, wonderful to have you in the class. Now pass the microphone back, because otherwise you might have some challenges with the question. If you want, we can stay on you. No. Okay. So now we have 2 of you. So if we want to store the information, what would be one way of storing the information for both of you at once? Sorry, I'm getting some feedback on the mic.
Do you have 2 separate lists? What are you saying? You have 2 separate lists for each person? Or what are you...
So you could have a variable name 1 and a variable name 2. And now, would this be... What's the problem if I want to represent the entire class full of people?
It would be difficult to have millions of lists.
Yeah, I'd have lots and lots and lots of variables. So we do have arrays. We could have one array with all the names, and then what would we have on top of that?
Array with the ages and the array from where we're from, all that.
So if you were designing a programming language, what might be a better way of representing a person?
If I was designing the language.
Yeah, you're designing the programming language. You get to make it do whatever you like.
I guess if I could, I'd be able to have multiple different, variable types in one array, or yeah.
You'd be able to store multiple things together.
Yeah,
and let's say that these represent a person in the class. What would you call this type? Because you're talking about a data type here, something that contains...
Like a student type.
Student type. Okay, so let's see if C has a way to do this. Thank you very much, and thank you, Laura, for your contributions, and happy birthday. I won't get the class to sing happy birthday, but maybe another year. So we've come into, we know why we can't use arrays, because arrays can only store a single data type, but we could potentially have multiple arrays, one for everyone's names, one for everyone's ages, and one for everyone's location. But this seems to be a little inefficient too, because it's not structured in a way that compares to the actual data that we're talking about. It makes much more sense to group a single person's information together than to group everyone's information for each of those different elements of the person together. So thankfully, C has a way to deal with this. And this way is called Structs. It is a new data type that allows us to group different items together. And let's go to a code demo in, we've got 5 minutes, and see how to make a struct. So here we have it, our solution to our data type problem of storing multiple things together. Here is a struct for, instead of a student type, we have a planet type. What we are going to have inside our struct is all the different relevant attributes that we're going to manipulate within our program. So if I wanted to make a student type, I would follow a similar syntax to what I have here for the planet type. So I'm going to create a struct. I don't know why the highlighting behavior has gone funny. Oh, I'm not sharing my screen. Oh, I know why. Give me a second. Advanced. Give me a second. The zoomies are having some trouble. There we go. That should be right for the zoomies. Yes? Yep. Okay. So this computer is behaving weirdly. We'll see if we can still make it work. So let's create a new struct, and this structs type is going to be, do not know what it's doing. We're going to make this a student type. This is the syntax for creating a type with a type def. Now, what you could still do is you could still do like that and have a struct, but having the type def at the start allows us to refer to it quickly and easily without prefixing it with the word struct every time we use it. And now inside our student, we might have age, we might have a string name, and you'll notice that I'm using a pointer here. We'll talk about that a little later. But we could also do name with a fixed size of 20 characters. And then I might have our origin as well. Now what we can do inside my function is we can create a new student. So this is now the type that we're creating. We're using the type that we've just created, which is a struct. And, oh, I'm missing a few close. This will be Laura. And then I can also add elements to Laura, fill out her various different properties. So I forget how old you were. Yell it out for us again. 27, okay. So I got 27 in there. Excuse the editing issues. And then, and where were you from again? Tassie. Oh, and I've got an extra. There we go. Now notice if we changed this to be a random variable name, this would still work. In this case, Laura was the name of the variable and not the name contained within the variable. So these are definitely distinct. Just because you call your variable Laura is not going to set the internal name value of that particular struct to the thing that you called name. For example, I could have also labeled this first name, and then it's probably a little clearer why I'd also need to label that first name. And with that short interlude into C syntax, we are ready to conclude for the day. The big takeaways for today were our lessons on string sorting and just starting to think about the very beginnings of structs. Tomorrow we'll go into these in much more detail, see how to use them in more advanced ways, get some advice on how to improve our syntax around them, and see them actually in action. And with all of that, looking forward to catching you tomorrow. Have a wonderful rest of the day and a very happy birthday. Thanks very much.